So now we're going to go over a few problems on dealing with these probability rules. The first problem we're going to look at looks at just how to calculate a basic probability, and the second problem we're going to look at looks at how to use the addition rule. So this question here looks at a survey of 1,121 adults, asking them how we should deal with the current energy shortage. Should we produce more energy? Should we just conserve more? Or should we do both? And then some of the individuals have no opinion. So we're going to ask some probabilities. If we were to select a person from random from the sample, what characteristic would that person have? So the first question asks, what's the probability that the randomly selected person is more conservative or responded more conservative? So there were 511 people that responded that way. So there was 511 possible outcomes to select one person that said more conservative out of the total number of people that responded, 1,121. And so we'll use those two numbers to calculate our probability, which is 0.4558. The problem wants us to round to 3 decimal places, and so I'm going to go ahead and do that and round up. So that's how you calculate a basic probability. It's just the number of possible outcomes in that event of selecting a person using more conservative over the total possible number of outcomes, which would be the total number of people that was polled. The next question then focuses on the addition rule, and we can tell that it focuses on the addition rule because it has or in the statement. So we want to know what's the probability that this randomly selected person responded both or has no opinion. So those are two disjoint probabilities. And we know that they're disjoint because selecting both and having no opinion cannot occur at the same time. And that's the definition of disjointness. So we can use the basic addition rule and just add those two probabilities. So when we calculate these probabilities out, there's 62 people that chose both out of the 1,121 people, and we can add that to the 35 people that had no opinion. And when we add those two probabilities, we come up with the joint probability of 0.086. And so that would be the answer to this question. This next set of problems looks at what happens when you roll a die 3 times. And remember that a die roll is independent of the outcome of the next die roll. And so we can use the multiplication rule if any of our problems asked for and. This problem is one of those problems. So the wording of this question says, what's the probability you roll all even numbers? So that implies the first roll has to be even, and the second roll, and the third roll. So the use of the word and in those statements implies that we should use the multiplication rule. So the probability that you roll an even number is 3 out of 6 because there are 3 possible ways that you can get an even number with a die roll, a 2, a 4, or a 6. And there are 6 possible outcomes on a die. Here I've represented the 3 different outcomes, and again I'm multiplying them together because I'm looking at the probability that I roll an even number on the first one, and the second, and the third, and that's why I multiply them together. So when I calculate this out, it's going to be 0.125 is the answer to this question. The next question also looks at 3 die rolls, but this time it focuses on the probability that at least one is a 3. And again, the wording at least one suggests that we should use the complement rule. So again, the reason why we use the complement rule is that it's sometimes difficult to calculate the probability of at least one because there are several combinations of ways of getting at least 1 3. You could have 2 3s, or they could all be 3s, or there could be 1 3. And so we want to calculate the opposite of that and subtract the opposite from 1. So the opposite of at least 1 3 is that none are 3. So the way that we calculate the probability that none are 3 is we look at the probability that the first roll is not a 3. And there are 5 ways you can get not a 3. You can get a 1, 2, 4, 5, or 6. So there are 5 ways out of 6 possible outcomes to get not a 3 for the first roll, and the second, and the third. So again, we're multiplying again. We can use the multiplication rule because these are independent events. Once we have the probability that none are 3, we can subtract that from 1, and that gives us a probability of 0.4213. This last problem then about die rolls also uses the complement rule, and you can tell you should use the complement rule because here it's focusing on the words not all, and it's easy to calculate the opposite of not all. It would be that all are 3s, and so again we're going to use the complement rule here. So the probability of not all 3s is exactly the same as 1 minus the probability of getting all 3s. It's much easier to calculate the probability of getting all 3s. It's just 1/6 times 1/6 times 1/6. Again, this is just the probability that you get a 3, and you get a 3 on the second roll, and you get a 3 on the third roll. And we could subtract this from 1, and our answer will be 0.9954. Now it's important to note the difference in the wording between this question and the last question. They look very similar and they sound very similar, but they obviously have given us different answers. So it's important to pay attention to the exact wording of these questions in order to make sure you're calculating the right probability. Pay particular attention to the wording when it says at least one, or some, or not all. Those are good indications that you should be using the complement rule. This last set of problems that I'm going to go over then focuses on car ownership and the need for repairs. So let's say you own 2 cars and you want to figure out what's the likelihood that you're going to need a bunch of repairs. So you go to a consumer organization that looks at how frequently cars need repaired. And over a 1-year period, 16% of cars need to be repaired once, 7% will need to be repaired twice, and 1% will need 3 or more repairs. So we're going to use these percentages to calculate the probability of different repairs for 2 cars. The first thing that we're going to do is we're going to assume that car repairs for 1 car is independent of cars repairs from the second car, and that's going to allow us to use the multiplication rule. So this first problem looks at the probability that both cars will need to be repaired. Again, we're going to assume the cars are independent, so we're looking at the probability that car 1 will need repaired and car 2 will need repaired. And so we can just multiply those 2 car repairs together. First, we have to figure out the probability that 1 car will need repaired. So we can just add together the different probabilities of needing 1 repair, 2 repairs, or 3 repairs. And the reason why we can add these together is because these are disjoint. If you have 1 repair, then you're not going to need exactly 2 repairs. So these are disjoint, and so we can just add them together. So now that we have the probability for 1 car, we need to calculate the probability that both cars need a repair. And so again, because we assume they're independent, we can multiply the likelihood that they both need repairs. We can multiply those together, and that gives us a probability of 0.0576. This next problem looks at what's the probability that neither car will need repaired this year. And so we're going to start by calculating the likelihood that 1 car does not need a repair in the given year. We can look at the probability of needing a repair. This we found in the last problem as 0.24. And so we're going to subtract that from 1 because the complete opposite of needing a repair is not needing a repair, and that's 0.76. The next step then is to use the multiplication rule to find our final probability. We want to know the probability that car 1 and car 2 both do not need repairs. And so because we're using the word and, we could multiply the probabilities for each car that 1 car does not need repaired. So we're multiplying those 2 together. The final probability is 0.5776. The last problem that I'm going to do then focuses on the complement rule, and we're going to use our answer from the last one to answer this question. So the question asks, what is the probability that at least 1 car will need repaired this year? So when we focus on the probability that at least one car needs repaired, there's a lot of different ways that one car might need repaired. So it's much easier to calculate the opposite and subtract that opposite from 1. So the probability that no car needs repaired is the complete opposite of at least one car needs repaired. And so we're going to calculate that, and that's actually what we found in the very last problem. The answer from our last problem is the probability that neither car needed repair, which was 0.5776, and when we subtract that from 1, we get 0.4224, which is the probability that at least one car needs repaired. The last thing that I'm going to go over then is that the notation for OR is commonly notated as this U-shaped symbol, and the notation for AND is an intersection, so it looks like an N without the little tail on it. This is more commonly used in math and statistics books, and I wanted to make you aware of that. If you happen to see these symbols, the U represents the OR and the N represents the AND, and so that'll be useful if you see that in other problems. So now that you've seen the probability rules at work, we can make the problems more complicated and go over a more general addition and multiplication rule that allows for non-disjoint events and dependent events. And that's what we'll do in the next video.